It's right there. I think it's 2.
Okay, let's get started. The class seems a little bit smaller. I know at least one person emailed me sick. I don't know if anybody else is out today, but it's still happening. People are still getting sick, I mean. Nothing new there. Oh, okay. So keep a safe distance then. Yeah, what you see right here is Chinche's comments just before class on this particular example. There's just a typo. This is the pulse train with DC offset, just doing the efficiency calculation. The typo that I made was not adding. I added 4 to 2 and got 7 instead of 6. So if you ripple that on down through the numbers, that comes out to 67%. Is that right? That's what you showed me in my office. Then the interesting thing in this example is if you invert the pulse train, and this I alluded to a little bit last time, if you invert the pulse train, then you get a much lower efficiency. And that has to do with the fact that when you're doing AM, that's the baseline, the pulse train, the way it's set up right now, gets to have, let's see, get this squared up in my brain here. Yeah. With the normalization, you force it to be, in this particular case, you force it to be -1 and 2. But then if you turn it around and do what's down below here, the pulse train is oriented the other way around. So now oops, it's not good. Now this point is the -1, and then this has to be 1/2. So it forces the average value to be much smaller because of the fact that you always have to normalize the negative. Oops, this was happening to me last night. My fingers come around on my touch screen, my knuckle hits it, and all of a sudden the thing goes scrolling away on me, and frequently has been known to go up to the first page. That's the constraint. And when you have a waveform that doesn't have a 0 average value, then you get this behavior. And that's what this example illustrates. So you drop from 67% down to 33% efficiency just because the pulse train is turned around the other way. It's not really that big a deal. Like I was saying last time, most waveforms, like speech waveforms, are gonna sit symmetrically about 0. This is will only be an issue when you have some type of a waveform that would be used in a radar signal or something that's very asymmetrical. Otherwise, it's not really an issue for amplitude modulation. I think I put the example in here because there's an example of this in the book, and then it's kind of like a loophole is what it amounts to. A waveform can be designed in such a way that you can get a more extreme kind of efficiency calculation. With regards to the exam, though, the types of calculations that most likely you would have to do would not be this sort of anomalous condition, but would more likely be what was in this example over here with the multiple sinusoids that we were talking about last time, where you've got more than one sinusoid, so the waveform, you don't know what the minimum value is going to be, and you have to go through and find it, and then you use that in your calculation. So this would be a more typical scenario. And if you can't find it, you can just worst case it, which the worst case on this waveform, I think we talked about this last time, if you have 3 sinusoids and the amplitudes are at 2, 3.5, and 4.2, and you don't have MATLAB handy to do the calculation, what is what is the most negative value that this waveform, or most positive value that the waveform can take on? Just, yeah, it's the 9.7 if you just add up the amplitudes. So it swings between plus and minus 9.7, worst case scenario. You might be thinking, well, how does this really work in practice? Speech is very random waveform. It's not deterministic. What really goes on in an audio processing system for AM radio is there's some sort of amplifier called a compressor amplifier that sits in front of the modulator and makes sure that the waveform stays normalized properly. If it's speech, they will compress it like crazy to make sure that it stays right at that normalization equivalent to the -1. And that's usually what you hear like in a sportscasting scenario. I don't know, some of you listen to baseball or any sports on AM radio. Have you ever listened where the announcer is continuously jabbering away and you don't hear really any background noise or anything? But then as soon as he pauses or takes a breath, you hear this gasping sound because the gain of the amplifier rises up to try to renormalize everything to get the level as high as possible.
So it's constantly varying?
It's constantly varying the gain to try to keep it at the constant, at the maximum amplitude level, because they're trying to get as much modulation onto the carrier as possible to ensure that you can hear it. Because if it gets too weak, then you know you're tuned onto a station, but the modulation is so weak that you don't hear it. And then, the theory behind that is that you won't listen to the station, or at least what I learned a long time ago, and this probably doesn't apply because talk radio isn't that huge, but they still sell advertising. So if a radio station is going to sell advertising, the advertisers want their ads to be heard. So they generally are compressed a lot, non-linearly processed, so they come through really loud and clear. Speech, like an announcer in a baseball game or whatever, you want that to be loud and clear. If it's music, though, you don't want it to be all compressed, because then the soft passages and the loud passages all sound the same, and then you'd say, this is really poor. And that's one of the bad things about AM radio, is that you have to play that game if you want to make sure it has the punch power to be heard. But on commercials on TV, the audio comes up too, right? Kind of for the same reason. I was told that the reason why that is again because the advertiser wants that speech to just come blasting away. You want to make sure the viewer hears the ad. The fidelity isn't as big a deal, maybe, necessarily. But AM radio in particular has this phenomena. So you have this nonlinear amplifier, and it's done with a feedback mechanism around a gain stage. So you regulate the gain of the amplifier to always put out the same constant value. So that's a combination of electronics and feedback and control. And I know it's not something you talked about in electronics, but you can make a variable gain amplifier where the voltage can be used to control the gain, and then you can have a power sensor on the output of the amplifier that just rectifies the output, creates a DC bias, and that becomes a set voltage that goes through a differencing circuit or a feedback amplifier, and then basically is like automatically raising and lowering the gain of the amplifier to keep it at a constant level.
So in actuality, you've got a signal and then you're normalizing it to that -1 value. That actually happens
in a real system. It's not necessarily -1, it's just some voltage level. In a radio receiver, you actually have another amplifier on the RF signal that comes into it called the automatic gain control, and it does the same thing, but it's on the receiving side rather than on the transmitting side, and that's to try to make sure that the signal into the envelope detector is about constant. Remember this? way back up here to these pictures to make sure that this gets driven properly, because if the signal was to get too weak into this envelope detector, then the diode wouldn't necessarily turn on, or you'd have issues with this circuit. Of course, it's done differently in modern implementations. This is kind of like the baseline traditional implementation with a rectifier diode. But that's part of the receiver, and that's done on the RF signal, or actually on the IF signal. We haven't talked about intermediate frequencies yet, but we're getting closer to that. So automatic gain control devices are there. When I was in school, and I was first working in industry at Motorola in Scottsdale, Arizona, my big baby, so to speak, was an AGC amplifier for pulses that came from a photo multiplier tube on this Lasercom comm link. So not only did I have to have a wideband amplifier that could process these 200 picosecond wide pulses, I had to regulate that gain to be a constant value, so I had to build this AGC circuit. And it was fairly challenging for me. It was definitely an electronic circuit design type problem. And if you have A to D circuits involved in digital processing, then it's even more of an issue, because you've got to make sure that the amplitude level that hits the A to D falls right in the dynamic range of the A to D. You can't have it be too tiny, or you can't have it be too big, because you lose out either way, either getting too much quantization noise, or you're saturating the converter and then it's clipping, and then that's ugly too. So it's actually, it's not something that has gone away. It's just something that you guys will only be confronted with when you are in a position where, you know, the job says you've got to figure out how to make an AGC amplifier work. It has an attack time and a decay time, which takes me back to the radio broadcaster. I can picture listening to a baseball game where they pause and the gain rises up rather slowly. Then as soon as he starts talking, it instantly re-regulates. So it has an asymmetrical time constant on the gain control. Most everybody acknowledges that you've heard that before, but has anybody not heard that or listened to an announcer? Okay. Sometime, it has to be a baseball game. You hear them talking, you don't hear any crowd noise, but then as soon as they stop, it's like somebody turns up the volume on the microphone and you hear all this noise in the background. As soon as he starts talking, that noise goes away, because he's talking and the gain is now turned back down again. Or if the guy's taking a breath, sometimes it's like it super amplifies their inhaling, because it's risen the gain way up because they're not talking, and then when they breathe in, you hear that really loud. Has anybody ever heard that?
I think I have. Sounds familiar.
It's like they're gasping for breath because the gain has come way up. Okay, getting back to where we're about ready to go into single sideband. In case you're wondering, I've posted up a set number 4, and I've posted up set number 4 solutions just so we can have them. So set number 4 has this Weaver's modulator on there, which is part of what is in the project. It's the exact same thing. So it was a homework problem, and then it gets sort of implemented as a simulation in the project. But I already posted up the solutions because my note at the top here says portions on exam 1 and portions of this are likely candidates for the quiz that will occur the week after next, like on the 21st, which is the Thursday before spring break. If we can make it that far. I'm just sort of laying out the roadmap a little bit there. I also put up the histograms for quiz number 3 and quiz number 5. Remember, quiz number 4 there wasn't because of the snow. I put those up today because my grader got me the spreadsheet this morning, and I figured I'll just process it. But she's not able to drop off the papers until later tonight. So if you're really anxious to get them, you can try to find me tomorrow. I'm probably going to be working on my book from at home or at Emergent or something. I don't know yet what it's going to be. But I'll have them here on Thursday for sure. There will be no quiz on Thursday, though. We're going to talk about the exam. for next week, the ground rules and what the topics are. It's likely, though, that I'm going to give you a mock quiz, a practice quiz, just so you can see another example problem of a type to be considered for the exam.
Will we have practice tests available?
Yeah, they've been up. They've been up there for over a week now, right? Some of you have probably studied them already. Or no? Has anybody looked at them?
I remember seeing them online. I didn't
Yeah, you go down into here. There's one from 2007 and one from the last year, 2012. And these are with solutions.
Awesome.
So they've been up there.
Did you say that one of them was going to have, was likely going to be more similar in content to what we had this year?
Yeah, but I don't know which. 2007 was more focused on Chapter 3, or Chapter 2, I mean, and a tiny bit of Chapter 3. And last year's had a heavier content from Chapter 3.
But that was because I think we were started earlier last year or something.
Something like that. I mean, I keep looking at the calendar saying we're a week behind, but then I keep thinking when I did my senior design projects class calendar, I had the semester ending a week early, and then I went back and looked and I said, no, it doesn't end here. It ends one more week into May. So that makes me think that there's 1 week additional after spring break this year compared to last year.
I think we started a week later.
It has to do with the holiday, but does anybody confirm that? It's a trivia question, I guess. Is there 1 more week this year after spring break than last year?
Extra credit points?
Nah. It'd be a question, though, you'd want to ask yourselves if it's true or not true.
By the way, spring break's almost.
Well, if you were at CSU or K-State, where my sons are, their spring break is coming up a week before our spring break.
Every other school but ours.
Well, it used to be if you were going to go skiing,
Makes travel cheap.
you'd want to have your spring break the week that no one else has spring break so that the ski slopes wouldn't be busy. But that's kind of hard to predict, I think. Somebody will be on spring break when we are, for sure, like the whole of Colorado Springs. So if you plan on doing something like that, you're going to be not alone. Okay, single sideband modulation. We started looking at this last time. The idea is to be bandwidth efficient, and although it's not an extremely popular scheme, it does introduce some mathematics and techniques that are useful even in this day and age. I mean, it's not the way to get necessarily the way to get bandwidth efficiency except for analog modulation, but it has some interesting mathematical techniques involved with it. So the idea is, looking at the single-sided spectrum, is to get rid of one of the two sidebands because they both contain the same information. So the picture here shows that you either get rid of the upper or get rid of the lower. And the Hilbert transform is the mathematics behind it. And like I was saying, maybe you're not going to do single sideband, but Hilbert transforming filters are definitely useful in digital signal processing based communications receivers. So what's special about the Hilbert transform? It sounds fancy and sophisticated. It is not like the Fourier and the Laplace transforms. It's not starting all over again. Really, the Hilbert transform is a filter, and all this filter does is shift the phase by 90 degrees. So this is the core, heart and core of the Hilbert transform. It just says the frequency response is minus j signum of f, and the signum, or SGN function, is also sometimes called the sine function, SIGN. And it's a function that's 1 when f is greater than 0 and minus 1 when f is less than 0, and it's not defined at f equals 0. So the minus j is the main thing, and the phase is an odd function of frequency, right? That's a property for real systems, and this definitely obeys that, because when f is positive, the phase shift is going to be minus 90. When f is negative, because of the minus sign down here, combined with the minus j, it's going to be plus j. So the filter has a phase shift. only. It doesn't. The magnitude response of the filter is 1. Now there's some discussion in the notes trying to go after what does the impulse response of this filter look like. And you would think that that would make sense. Let's just find the impulse response so we can send signals through the filter. So I went through some of the math like they do in the book, but when you get done, you get this not very pretty result. It's not nice looking, because if you have to do an integral that involves something in the denominator like t, that's a singularity, and that makes for an ugly integral. I don't know if you can think back to calculus, but I can remember spending a unit or two on integrals that have singularities and finding that to be just kind of a pain to have to go through. It's like going in there with the tweezers and saying, okay, how do I manage this condition? It's just kind of frustrating. So the better approach is to stick to the frequency domain. And that's kind of that's the approach. And then there's going to be a property that we're going to look at that will make things more clear. But the whole development we want to go through will be based on a frequency domain argument. So I don't want you to go off the deep end and worry about having to do a convolution integral with a t in the denominator, because it's not going to happen. It's in my notes, but I'm not emphasizing it. I'm wanting to make it clear that I'm de-emphasizing it. One of the immediate observations, though, is that if the Hilbert transform shifts by minus pi over 2, that would say that a double Hilbert transform would just be an inversion, because if you pass through two Hilbert transforming filters, you're going to shift by minus pi over 2 and then minus pi over 2, and that's going to be a minus pi, and that's going to invert the signal. And you can see that by just taking and squaring the frequency response, as if you were cascading two filters, right? You multiply h of f times h of f. Getting at some baseline signals, though, like a cosine, omega naught t, send that through the Hilbert transforming filter. Rather than doing the convolution, we'll just do it in the frequency domain. So take this guy, Fourier transform it, get its spectrum, and then pass it through the filter, the signum function, and use the definition of the SGN function, and we get a minus j and a plus j. And then you can put that back together again using this Fourier transform pair. And when you put it back together again, sure enough, you get a sine, which is no real surprise, because you already know the trig identity. You know that trig identity, right? So formally it says the big hat sitting on top, or the giant circumflex, that's the math term, remember, of cosine is sine. And then if you Hilbert transform sine, you're going to shift the phase again, and that's going to take you to minus cosine.
So the big funky hat thing just means minus pi over 2?
Yes, on a cosine. If it's a broadband signal, then it's more complicated what it does. But yeah, you can call it a funky hat if you want to. You can call it a circumflex. That'll get raised. That's what it's called, and that's a weird name. In the typesetting language LaTeX that I use to write the notes, it's just called hat. So I type a / hat, curly braces around it, and it puts a hat over it when I compile it. But as Dr. Ziemer trained me on many years ago, it's officially called the circumflex, which, it's kind of a long name to have to write out. Mathematician stuff. Look that up on Wikipedia, I guess, if you're interested. Okay, what are some properties of the Hilbert transform? Because the magnitude squared of the filter's frequency response is 1, the energy or the power in the signal is not modified when it goes through a Hilbert transforming operation. But the signals do become orthogonal. And a simple example of that is if cosine becomes sine, sine and cosine are orthogonal, right? Because of the 90-degree phase shift. But in general, any signal that goes through a 90-degree phase shift becomes orthogonal. That one's not that big of a deal. This one right here, though, is probably, this is the most important property for our applications. And we'll be utilizing that in some developments that are coming up here, and if there's some modeling in the receiver, this gets utilized. And what this property says is that if you have a signal m of t that's multiplied times a wideband signal or a high frequency signal c of t, and for our applications we can think of the c being like the carrier, then if we take the Hilbert transform of the combination or the product, you instead get just the narrowband signal, like the message signal, m of t, times the Hilbert transform of the high frequency signal, or high pass signal, or in our case the carrier. So the most common application would be in a modulator, let's say where we're doing something with the Hilbert transform identities. Hilbert transform m of t times cosine omega naught t, as long as if that's m of f right there, and the carrier frequency f naught is greater than this w, then that says that if you Hilbert transform that signal, in other words, if you Hilbert transform the signal that's been put up on the carrier in double sideband form, because that's what happens if you take m of t times cosine omega naught t from the modulation theorem, we're going to get something like that in the frequency domain. So if you Hilbert transform that, the phase shift applies to the carrier only, it doesn't apply to the message, so you get m of t times the sine of the carrier, because the Hilbert transform of cosine is sine. Now right now that doesn't seem all that exciting either, but it's what's going to come up in a few moments here to actually develop the modulator that you're going to see how that works out. Okay, sort of a sideline topic, and this is more applicable to modern day DSP type ideas, is something called an analytic signal, and then we get into what's called the envelope of the signal. So an analytic signal is formed by taking a real signal, x of t, and adding to it j times the Hilbert transform of the signal. The envelope of this signal is the magnitude of z of t, and we'll be looking at envelopes a few more times throughout the semester, and I may give another handout on it if I can put it together. I wrote about envelopes in the book that I wrote, and I came up with an easier way to explain it than what I have in the notes, because I wanted to keep it simple since it was for dummies. I'm not sure I'm going to go do that or not, but it is useful to understand some envelope modeling. But at any rate, it's the magnitude, and it's very similar to the double sideband and the AM envelopes that we've already looked at. And if you're saying, what envelopes did we look at? I can dial back here and I can say, the red is an envelope that we looked at, right? I called that the envelope. And then for double sideband, there's the envelope. It crisscrosses through the positive and negative sides of it, but that's the envelope. And we'll be looking at that again when we're looking at this double sideband, and then we'll look at envelopes again when we're studying interference a little bit later. This is a complex signal that has an envelope. So analytic signal, interesting property of the analytic signal is it has properties, it has single sideband-like characteristics, and it's not really a surprise, because if you look at this analytic signal, we see how we're going to develop single sideband. There's a connection there. So if there's a plus sign in here, which is the way it's been defined initially, meaning the positive analytic signal where you add J times the Hilbert transform, you just simply jump to the frequency domain again. Notice how I'm not going to deal with any convolutions or anything like that. I'm just going to look at in the frequency domain. You look at what goes on with the Hilbert transforming filter is right in here, times the spectrum x of f. And so we've got a minus j times a j, so that's what? Minus j times j is 1. So there's a 1, and then you just have the SGN function. Well, the SGN function is going to interact with that constant of 1 because it says we have a signal that's always 1, like that. Then we have the signum function, it's like that. And if I do the addition of those two, what do I get? I get a signal now that comes along at 0 and 1, but this is in the frequency domain, so I shouldn't have been saying signal. So it's annihilating the negative spectrum is what it's doing. It comes along, this analytic signal has got a spectrum that's only got content on the positive side. And this is a 2 in here now, because this was a 1.
What's those two blue lines?
That's just to say I'm going to do addition.
Okay.
So one waveform plus another. Added up. So only positive frequencies present. If you define the negative analytic signal, it flips it around the other way. So now you just have the negative frequencies present. So this is the sort of the family of the family portrait, I guess. The signal, positive analytic signal, negative analytic signal. Like I said, in digital signal processing and receivers, this is sometimes this property is utilized. And basically what it allows you to do, if you can build a Hilbert transforming filter, and MATLAB has that built into its signal processing toolbox, you never had a reason to do it, but in real-time DSP we've implemented them, and you can implement them for, say, work projects. I've done it when I worked at Real-Time Logic. It was a possible architecture that was going to use Hilbert transforming filters. What you can do is you can bring in a real signal from a single A to D, and then you can get access to the signal and the analytic signal by post-processing with a Hilbert transforming filter and then a straight-through path. And what it allows from an architecture standpoint is you can get by with only one A to D as opposed to two. It's just a technique that allows you to do processing at the front end with less hardware or matched hardware. Because if you have certain types of sampling front ends for radio signals, if you have to have two A to Ds, one of the issues that comes up is the matching on the A to Ds. Will they be perfectly matched? They won't be. And will they be matched over temperature? They won't be. Will they age the same? They won't be. But if you can get it done with a single A to D, then you can form what's called the in-phase and quadrature signals from a single converter. And one, like I said, one approach is to do it with the Hilbert transforming filter. And then there's another approach called IF sampling, which is probably a little bit more popular these days, but it just depends on how the front end is to work. Okay, so jumping back into the book now, the single sideband development is based on the analytics, well, based on the Hilbert transforming filter idea. So right now, we're going to form double sideband, and then we're going to send it through this magic filter, which only lets pass the upper or the lower sideband. So I've got a kind of a graphical approach to getting the solution here. The graphical approach starts by saying, okay, here's my two-sided spectrum of double sideband. If I'm going to go after the lower single sideband, so it's called LSSB, What I'd like to do is come up with an effective filter that's that red dashed line that the signal can go through this filter, and all that's going to come out is the lower sidebands. Does that make sense? So your instinct based on what you know from electronics and signals and systems is, I'll just build a low-pass filter that cuts off at FC or does something along those lines, and I'll get the lower sideband that way. And that could work. That could work too. But the mathematics of the Hilbert transforms allow you to get a very precise relationship here, and that's what we're going after right now, is to just show analytically how you can write down exactly what the single sideband signal will be. So the way the development works is you form one filter which is a signum function shifted to the left by FC, and then put a scale factor of 1/2 on it, and then subtract from that a signum function filter that's been shifted to the right in the frequency domain out to FC. And when those two add together, the 1/2 in here and the 1/2 in here is going to form the 1, and then the minus 1/2 and the plus 1/2 out over here give you the 0, and likewise the minus 1/2 and the 1/2 in here gives a 0 out over there. So that synthesizes the frequency response that we're looking for. Okay?
So is it better than a low pass because of that, or because you still have cutoff issues, right?
Exactly. We'll see.
Okay.
And then when you implement this thing in the DSP for the project, you'll see there too that
You said it was better
the Weavers.
mathematically, though?
Yeah, this gets you a mathematical representation that is exact.
Okay.
One of the things you have to realize is that, well, it depends on what type of engineer you classify yourself as. You classify yourself right now in your life as a hardware engineer or a analysis systems type engineer. When I was in school, I considered myself a hardware designer. I just wanted to build things that work. I wasn't interested in as much math, modeling, and analysis. I left that up to somebody else. And when I worked in industry, that was a divide that I was in. I was a board designer. I was responsible for getting modules to work, plugged into the chassis, and delivered to the customer. There was another world of engineers on the other side of the fence that were the systems modeling types that worked at the computer all day long and did the modeling and said, this is what you have to do. This is what my equations say you have to do. And us guys that were the hardware engineers would always say, yeah, right, you don't know what it's like to build something. Your equations say this should work, but you don't know what the technology limits are. So I sat on that side of the fence. I was on the hardware side. Then when I went to graduate school to get my doctorate, I became the analysis and systems type engineer. So I sort of defected to the other side. But I still like building hardware too. So I think actually if you can have a respect for both sides. But when I worked at Motorola, there was definitely the two sides, and they were at odds with each other at times. So what do you guys think you are? I mean, have you thought about that, or? I'd say most people in school probably are hardware, because I know that from talking to freshmen trying to figure out why we didn't have people going to an EE for quite a number of years, they were all going to mechanical, and I was asking them on freshman orientations why, and they said, well, I can see it, and because I don't want to do software is what they also told me. And I said, well, doing software is something you can't avoid no matter where you're at in engineering. You're going to have to use modeling tools. But I think generally what happens, though, you start doing hardware, and then as you grow up more, you get the option of staying with hardware or being more analysis and modeling oriented, because you're going to become the senior engineer that's going to have to spec the project and work with the customer and define the requirements, and then you just naturally gravitate more into the architecture and modeling phase. And then you get some junior engineer to come work for you, and you say, oh, you don't know all this math and all the system stuff, you can design my board or You know, it just is. It's just a natural the way things work. Plus, if you're going to have credibility, I'm on a soapbox right now. If you're going to have credibility when you're a senior engineer, you've got to be able to tell your junior engineers, I was where you were. Trust me, you know, I was in your shoes. I know what it's like. Would you want to work for a manager that had never been there and done that? I know I didn't want to do that, because can you trust somebody like that? I mean, that's what I felt like. If they haven't been in my shoes, which is why I guess I didn't like the systems engineers at Motorola, because they were probably my same age and they had never built hardware, and I thought, how do you know what this is like? But they considered me to be ignorant of the math, so we were like that. We were at odds with each other. We were orthogonal. At any rate, well, orthogonality means you have nothing in common, right? However, I could go off and tell you more stories. Since I married an engineer, not an electrical engineer, my wife and I don't talk about work. She's a programmer, but that's a good thing, I think. If you're going to marry someone who's also an electrical engineer and you're both going to be hardware engineers, you may have problems in the future. I don't know. Okay, so this is a synthesis, and what the long roundabout way was to say we're just synthesizing a theoretical expression that will be ideal in terms of if we can implement the Hilbert transforming filter. So now that we have what this filter looks like, this is what the filter looks like. This is actually the it's the LSSB filter. Lower single sideband filter. Now we can go ahead, and this is still avoiding the convolution integral, staying in the frequency domain. Just take our double sideband signal and multiply it times this filter. It has to work, right? We're just using the convolution theorem and multiplying them together. And now we've got a bit of a mess. If we carry out this product, we have a total of how many terms? 4 terms, right? So the easy terms to go with are the terms where the signum is not switching at the same location as the spectrum on M is. Because M is centered either at FC or minus FC. So if I was to draw the picture of that in there, M is here and here. The signum function in some instances is going to come along like this, and in the other instance let's see, did I draw that right? Drew it backwards. Sorry about that. This one is switching over at minus FC, so it's coming down like that. And the other one is switching at plus FC, but it's got the minus sign on it, so it's going to come out negative. So when I do these 4 terms, the first terms that I want to consider are the ones that don't have the signum function splitting my signal spectrum down the middle, my double sideband spectrum. So if you look at it carefully, as I've got it written out, I've got all 4 terms written out right here. The first terms I want to consider would be this one and this one, because those 2 terms have the signum function switching well away from the spectrum piece. So these 2 terms give me these guys right here, which are the double sideband terms, actually. They're the original terms that we started with, except there's a 1/4 on there instead of a 1/2. And then these terms, which are switching at the same spot as the spectrum is centered at, are these guys down here. And I can't get rid of the signum function immediately, so I have to just hold on for a second and do some fancy footwork with some Fourier transforms. Actually, it's going to be the Hilbert. This is how the Hilbert transform enters the scene. If I go look at that second term, the one that I have the blue arrow pointing to, I've got operations that look like this going on, except that I have f shifted to fc or to minus fc, but it's that type of transform. So if I consider how the shifting of the frequency axis comes into being in the time domain, that's multiplying by in either a positive spinning complex sinusoid or negative spinning complex sinusoid, right? From the frequency translation theorem. So I can decompose the last two terms, these blue terms in here, using this identity right here, which was developed using the frequency translation theorem and the the fact that the Hilbert transforming filter times a spectrum, times a signal spectrum, is going to be in the time domain the Hilbert transform itself, m hat of t. So finally what you end up with then is you end up with those last two terms involve just the Hilbert transform and the sine carrier as opposed to the cosine carrier. So when you finally put it all together, and I realize I'm going kind of fast, but the blue box is the facts, it ends up pretty nice. So it's just m of t cosine, that's the original double sideband, and then the m hat sine term. So it's got to be that that term makes single sideband. I mean, the first term is the double sideband. So the inclusion of that second term, where you've Hilbert transformed the message and then it used a sine carrier, is what allows you to get the single sideband. And if you were to go through the other scenario of synthesizing the filter that would throw away the lower sideband and keep the upper sideband, it turns out that it's just a change of sign in there is all it takes to go between the two modes of operation.
So if you plotted that in the frequency domain, the LSSB, or either one,
Mm-hmm.
you should see it being split so that there's only one.
Yeah. When you build the model up in MATLAB, you will have a switch on it that you can throw the switch effectively by doing a sign change in this Weaver circuit. But I've asked you to write it up as a module. It has a parameter that you enter into it, so you'll just enter a parameter like a +1 or a -1. I forget how I specified it. That will do that, and then you can use a tool, a spectrum analyzer tool in software, to look at the output spectrum, and you'll see that it will flip from upper to lower. Now, it won't be perfect, because the filter is finite order filter, but it will definitely switch it. So these two equations lead to what traditionally is called the phase shift modulator. So the phase shift modulator is just a direct implementation of those equations. It says that you've got m of t comes in, you bring it up to the cosine modulator up here, you take it through the Hilbert transforming filter to let it be m hat of t, you multiply by the sine and the cosine, and then you add them together, and then you just have a switch over here that either adds or subtracts. And for microwave circuits fans, this is the quadrature hybrid that you learn about if you study RF circuits. That's just a a component that a microwave circuit designer can build. You can buy it off the shelf for your design. When I worked at Motorola, we bought them from a vendor and put them right on the boards, the circuit boards. But it's an element that has a very precise control over the phase shift, called the quadrature hybrid or 90-degree hybrid. So that would get you the modulator directly, and this is one form of single sideband modulator then. So you have to do the Hilbert transform down on the message signal to make this work. To demodulate a single sideband signal, you can just use the same old coherent demodulator. Remember when we first looked at this, we found out that this works for double sideband, it works for AM according to that homework problem, right? And it works for single sideband. The coherent modulator is pretty robust. You can do a lot with it. And you can do a lot with it for digital signals too, digitally modulated carriers and so on. Pardon me?
Sorry, why is it 4 times? Is that just to compensate amplitudes?
Yeah, exactly. It's 4 times because a good way of thinking of it is because with the single sideband filter on there, the signal of interest has actually been reduced in effectiveness by 1/2 because we put half of it into the cosine and half of it into the sine. Effectively, I think that's one way of thinking about it.
But does that double the amplitude?
No, because a piece that we're going to get back out from the second term, in other words, when we go through the demodulator, this term right here is not going to bear fruit, useful fruit. It's going to be what's called the crosstalk term. And this 1/2 wasn't present in double sideband, right? The 1/2 is on there because we have this component and this component together. And remember, the Hilbert transforming filter does not change the power spectral density or the energy spectral density. So it's just what we can recover out of the signal is 1/2. So the 4 is on there to gain scale it. But again, this is the systems analyst view of things. If you were a hardware designer, you'd say, I don't care about a 4 or a 2 or a 1 or a 3. I put gain scales in that make my electronics work properly. That makes sense, doesn't it? I mean, you know what the rails are on your electronic circuit design. You don't want to overload it. You don't want to underdrive it because of noise and things. So these scale factors are just artificial in the modeling sense. They're just to make it come out looking pretty or cute, however you want to describe it. If you haven't figured that out, now I'm telling you it's so. Math can be beautiful, right? So you make all the numbers work out so it looks picture perfect. But in hardware, of course, it's going to be whatever it needs to be within a scale factor. So you go through the math of multiplying by the coherent reference, which is this guy over here. And now I've already built this up, so I've got this factor. And this is thrown in to model it as just saying, let's not do this twice. Let's just throw in that factor that I can either set to 0 or let be present. So I'll build up a model right away to handle the non-coherent aspects if I want to. I mean, why not? We've seen it before. Just throw it in there, and then I can either ignore it by setting it to 0 or see what it does, and I'll have that handled right away. So multiply that out. We get double frequency terms, and then we get the difference terms. So we get sum and difference terms. Some terms, here and here. What's going to happen with those terms based on previous experience? Where do those terms go to? The filter takes care of them. The filter takes them away. So you get used to that idea in this class now. We know how the frequency domain works, and as long as those double frequency terms can be separated from the baseband terms, which they can be if the omega c is high enough, and then 2 omega c is even higher, we just assume we have a low-pass filter that can do that separating. I could go on a soapbox about that too. Why is Fourier analysis and all this other stuff valuable? Because it now gives you this power to just say, oh yeah, I can do that because I understand how the frequency domain works, right? If you take yourself back 2 years in time in circuits or something, and you'd say, I don't know, because you don't know at that point. But once you have enough power and confidence, you just defiantly say, I know I can do that, to within limitations of how well I can build the filter. So those terms are gone. And then we're just left with the m of t cosine theta of t, which you're supposed to recognize and say, that's the one I'm looking for, right? Because there's m of t, the message back, and if theta goes to 0, cosine of 0 is 1. So that's the keeper signal. And then in this case, we've got this other signal on there, m hat of t, the Hilbert transform of the message, and the sine theta of t. And if, say, theta is small or slowly varying, then we can use a small angle approximation for the sine and say it's just the angle, and the small angle approximation for cosine would be it's approximately 1. So we just have the message plus this term that's referred to as crosstalk.
How do you get rid of the crosstalk?
Have a coherent carrier, so theta is 0, right? Or theta is just small, right, in the small angle approximation, so that'll be small.
Don't you still have that overt signal in there that you don't want?
You have it in there, but make that term much less than 1, and then it's just squashed down. Squashed down on a dB scale, I guess, is the way I'd think of it, because decibels is popular terminology. Like if we can squash it down to be 60, 70, 80 dB down, we won't notice it. If it's only down 20 dB, it's not that noticeable in speech. Okay, what about envelope detectors? Can we do something with that? It turns out you can. We have the envelope detector for AM. This is a new concept of the envelope detector. It's called carrier reinsertion. What it says is you take your signal and you throw a carrier back onto it at the receiver. So the receiver is sitting here, and rather than multiplying, you add a carrier back in that has an amplitude k, and then you go into the envelope detector that we've looked at before and try to see what comes out of that. So if you go up to the modeling of this, we're just adding a pure carrier back in, and right now I'm going to assume that it's coherent so that it can add in phase with the cosine term that's coming in, but in a second I'll not make that always the case. And then we get the plus and minus for the upper and lower sideband cancellation with m hat of t. So now what we need to be able to do, we need to be able to do what's called an analytical analysis to see the envelope. So we have to find the envelope of our signal.
Isn't it right there?
The envelope can be obtained from up above you, right?
Well, because above is a D equals that. So isn't that the envelope?
Well, E of t is not the envelope.
Oh.
Remember when I drew those pictures and looked at those pictures, that red waveform that was writing on top?
Okay.
The red is the envelope, but the real waveform has got all that blue stuff filled in between. The envelope is what the envelope detector extracts, though. So how do we get the envelope? One set of modeling is right down below here, where I write it out in that fashion. Another set of doing this goes back to the phasor addition formula, which this is going to be a stretch, but in 2610, one of the very first big math things you learn is the phasor addition formula. Now the question is, how many people remember that fairly well? Can you remember it? Okay. So I could take this analysis approach that I have right here, or I could go pull up a blank sheet and say, remember the phasor addition formula. And I've got my clock running. Or I could just say, believe me, it's this. What do you want to see? You can see it right here, but you could get this from the phasor addition formula just the same. Maybe you see enough of it from here. I don't know. All I really have to do from the phasor addition formula, when you did the phasor addition formula, you had to have it all in cosines, right? So if I modified this to make this be cosine omega ct plus pi over 2, right? That's all I'd have to do. But then if I wanted to do the phasor addition formula, it would say I'd have to pull out, in the phasor addition formula, it would say that I have to take a of t squared plus the component that's going to come out from this second cosine term in the phasor addition formula would be the minus b of t. And then in order to handle that minus pi over 2, I have to put in minus j pi over 2, right? And then I have to do some other factoring in here. Namely, I'd have a j that would come out of here, so I'd get a j. This would come down to be j b of t, because the e to the minus j pi over 2, that is a minus j, right?
Yeah.
And then the minus j with the minus sign becomes a plus j. Then the phasor addition formula says that I have to take the sum of the squares of the real and imaginary parts to form the envelope. So it'd be a squared plus b squared of t in this case. So I guess I sort of got there quickly, kind of with a sleight of the hand maybe. So that's where the envelope comes from. So it's a squared plus b squared of t. I had a picture to try to draw what's called the resultant, but I like this idea better. I mean, I like the phasor addition formula because it's getting mileage out of something you learned already. But you have to take yourself back in time. When you learned the phasor addition formula, the a of t and the b of t were just constants. They weren't functions of time. But it works in any case. The idea is that we can factor out a common frequency. So here we have a common frequency, and then we have another common frequency sinusoid over there. So we get at the envelope then as being the square root of the sum of the squares of a of t and b of t. And how does that apply here? Well, up in here, this is the a of t, and then the b of t is right in here. But if you go ahead and leave the cosine theta naught terms in there that we had in the earlier analysis for the not perfectly coherent, then you actually have to include a cosine theta t and a sine theta of t. That's kind of not shown in the analysis, but that tweaks it just slightly. So when you pile all this stuff together and solve for the envelope with theta of t equaling 0, then you'd get this form right here. And it looks kind of messy. I say it looks messy because whenever you have a square root of something where it's time varying on the inside, it's like, that doesn't look pleasant at all. How can I deal with that? But there's something called the binomial expansion, which, have you ever heard of the binomial expansion? In fields and waves maybe, or where? Have you seen it before? Okay, that's right, in problem stats. It's used in fields and waves as an approximation field at a distance from a point where you've got some symmetry like cylindrical coordinates or something. I mean, I can remember it from doing fields and wave stuff. Binomial expansion is this thing right here, though. 1 plus x to the 1/2 is approximately 1 plus 1/2 x when x is much less than 1. So the way we can get x much less than 1 is you make k large, and then you factor k out from inside this radical, and then you'll end up with a 1 over k sitting inside of this term. So that will become the small term, and then the large term will be this one over here in that binomial expansion. So then what you're left with is this. Now granted, this is large. Oops. And the term that sits next to it is small, but it does pull it out. I mean, it pulls out those two terms, and the Hilbert transform term, m hat of t, goes away. Now, if you go through the analysis where you have fully non-coherent, which is the next thing I had in here, where it's actually got a frequency error, it's kind of messy. So what I did for that was, rather than do that with a general message, I said, suppose the message is just a cosine signal at omega m, and suppose the reinserted carrier is just got a frequency error rather than a theta of t. So it's just tweaked in frequency from the coherent value of omega c by delta of omega. So you go through this envelope analysis, grind through the same stuff we just went through, and what comes out of that, I'm just sort of skipping some of the steps, what comes out of that is this equation right here. So you get back this large bias term, k, from the carrier reinsertion, and then you get, for the message, you get almost the message back. You get the message omega at omega m, but then it gets shifted up or down in frequency by delta of omega. Now remember when we did demodulation of double sideband in the demo I ran in class last week, the two spectrums of the message, one was shifted up, the other was shifted down, then they were superimposed. So we were hearing two tones at once, a high shifted and a low shifted, and if they got close to each other, like with the speech, it just sounded kind of warbly and garbagey sounding. In the case of single sideband with this envelope detection and carrier reinsertion, we just get one copy of the message shifted in frequency. So it just gets shifted up or down. It doesn't get up and down at the same time slapped together. So for analog messages, this is more intelligible because we're not having the two things superimposed. So we hear that discordant sound of, the speech shifted up and the speech shifted down superimposed. We just hear it shifted high or low.
So single sideband has less instances of error. Why would you use double sideband type stuff?
Why would you use it? Because it's simpler. This requires more hardware in the receiver. And, I didn't mention this fact. The fact that you're sending two sidebands, it takes up twice as much spectrum, but it makes the signal more robust in a noisy environment. We're more susceptible to interference when we have single sideband just because we're only occupying half as much bandwidth. We don't have redundancy or extra protection. But there's always a trade-off there. Just like, in anything you design, to have more robustness, you end up costing more, using more power, using more spectrum, you name it, the list goes on. So there's never an easy way of getting something for free, right? You just have your different trade-offs. Which would you rather have? And the telephone company investigated this many, many, many years ago. They said they had a closed environment. They could do it. They didn't interfere with themselves if they designed their electronics properly, and they needed to get twice as many voice channels in a given set of bandwidth. So they did it because it got doubled the capacity. Today, if we would have been starting all over again with fiber optic cables and everything, we'd probably say, not a big deal. Voice is such a tiny amount of bandwidth compared to, the megabits per second we demand with streaming video and audio type stuff. Because speech is narrow band, it's only 4 kilohertz wide for speech grade audio. Don't sweat the details. We'll just use the bandwidth because the fiber supports it. But back then, they had to carry everything across the country in microwave links, hop to hop, city to city, towers and things. So it was an investment that they made to make this work. Amateur radio definitely uses this, and I first got exposed to this when I was very young because my father talked on single sideband all the time, shortwave and bands and things. People still use it around the world, and single sideband is still part of that. It's more efficient. You get twice as many users on the same band of frequencies. Okay, we are out of time. This next topic we're not going to go through, vestigial, because this is definitely not too popular anymore. It's sort of a hybrid between double sideband and single sideband, and it was used for NTSC TV, which is now extinct because we have HD TV take its place. There's still some properties, I think, of vestigial sideband that are around, but I didn't talk about it last year, and I'm not going to talk about it this year.
So
we're going to be on to this topic, though, frequency translation and mixing. So what would you like to have a quiz on? A mock quiz, that is. Something with single sideband? That's what
probably what we just did, yeah.
That's what I'd like to do. I just thought I'd ask since it's a practice thing.
And on Thursday, since we have our test on next Tuesday, are we doing a review? Or
Yeah, we're going to talk about the game plan for the exam. So I'd like it if you would take a look at the old exams, and we can.
So are those
more
things designed for your 2.5-hour classes, or?
No, I mean they were designed for the 2.5. Yeah, you can, because I would usually lecture part of the class,
Okay.
and then we would go off to do
So
the
those are
exam.
realistic ones
They're realistic.
for what we have.
I may have to pay more attention to some details, but they are. We'll get in here. We'll get started immediately. So Professor Araujo is hanging out. I'm gonna.
No, they were well out of here today.
Okay. And I know that we have more time at the end. So if you want to be intelligent about this, I'll take advantage of that extra time. But that means don't plan on dashing off immediately, because I know no class comes in here until 4:45.
Right.
Now on Tuesday I do have another class that meets, but I can be a little bit late because they're in the lab working. We'll maybe talk more about the project too, now that we've gone through the single sideband stuff. And for those watching the video, just sit tight. I'll eventually, well, you won't see it till you see it, but it'll eventually get up there.